Welcome everyone to a new young session within our Machine Learning Needs Mathematical Optimization seminar series. We're very pleased to be back and also see so many participants today. As always, we're going to have 3 speakers and all the questions would be asked at the end, but if you have some urgent matter, you can always write it in the chat. So our first speaker is Alexandre Forel from Polytechnique, Montreal, and he's going to talk about explainable data-driven optimization from context to decision and bargain. So all yours. You have to unmute yourself.
Okay, thank you. Yes, thanks a lot for the introduction and for the invitation. I will now share my screen. Can you see the presentation?
Yes.
Okay, perfect. Yes, so it's my pleasure to present our recent work today on explaining data-driven decisions. This is joint work with Axel Parmentier, who is at the École des Ponts in Paris, and Thibaut Vidal, with whom I do my postdoc in Polytechnique, Montreal. So we are working on explaining data-driven decisions. So by data-driven decisions, usually we mean that we are making a decision in an uncertain environment and where we don't know the future, but we maybe have available some contextual information, auxiliary information that can inform us and help us to make a decision. So for instance, if we are managing our inventory or trying to find what is the best delivery route, maybe we do not know exactly what will be the demand or what will be the travel times to go to our customers, but we can use some indicators, some auxiliary informations, such as weather information or market indices, maybe recent information about the traffic conditions, and try to use this data to make a decision. So what it looks like is something like a decision pipeline that is shown here, where we have some historical data. This can be contexts we have seen in the past, so this will be X, or uncertain parameters we have seen their observations in the past in this specific context. And what we can do is to first train a machine learning algorithm that will now predict for any context some kind of intermediate inputs that we will use in an optimization model and finally find our decision. So what we want is to try to provide a bit more explainability to these pipelines and to connect the decision with the contexts. So usually when we develop an optimization solution, we have an iterative process. Usually we start from data. We will maybe refine our prediction model or machine learning model, refine our optimization models, try to find what are the constraints and the objectives, parameters, and so on. And a typical solution situation that may arise is that once we have this first version of this pipeline, we can find what is a decision, what is our solution. Here it will be, let's say, Z0. But maybe in the past at our company, we would have done something different. So maybe in the past we were doing Z alternative. And the question is, why are we now doing Z0 and not what we were doing in the past, Z alt? And to explain this, we will try to have focus on the contexts. So maybe in the past, the context was not very well reflected in the decision. Maybe now our decision Z0 better reflects the context. And to try to understand this, to explain a bit how does the context drive the decision, what features drive the decision, we will have try to derive a counterfactual explanation. So try to find either another context for Z alts in which this decision is now a better decision, or maybe it's an optimal decision. So counterfactual explanations have been studied quite a lot recently in the machine learning literature to explain the prediction step here. So how does the inputs lead to a prediction? But here we are really focusing on the whole pipeline from the context to the decision. So maybe an example here will make things clearer. We are adapting the real-world case study from Calus and Mao, where they try to find a shortest path from the east side of the Los Angeles downtown area to the west side. So we have some historical data available, some contextual and travel time informations, and we can train machine learning algorithms, say random forests, and try to find the shortest path. So we are in a given context shown here on top, So it's around midday. We are Tuesday of November, and we have some contextual information. And in this case, we find the optimal shortest path to take the north route here, shown in blue. And maybe in the past, we were actually doing another route. We were taking the south route here. And so the question is this south route good in other contexts? Is it even optimal in another context? And we find this explanation to say yes. And in fact, we just need to change one feature. So if the time of the day were in the morning, now it is the south route that becomes optimal. So we see here how the counterfactual explanation of the decision shows us what feature is currently driving the decision. So our focus in this work is really, well, how do we find these explanations? How do we find them for different machine learning models and different problems? So we are working with contextual stochastic optimization. So formally, we are trying to find a decision, Z, that minimizes our expected costs. And here, the expectation is conditioned on the context being the current context we are in. So we minimize our cost with regard to uncertain parameters Y in this specific context. And we have available historical data. So we need to solve this problem, but we do not know exactly, well, we don't really know in general what is the distribution for Y or X or their joint distribution. So we use the pipeline proposed in these papers, that is to solve, rather than to solve the sample average approximation of this problem, we will replace the expectation operator by weighted average over the historical observations. So we find a decision that minimizes the costs for all the previously realizations seen of the uncertain parameter, and we assign a weight to each observation that depends on the contexts. So you can think about these weights as measuring how important is this past observation I in context X. So higher weights will mean that we give more importance to these samples. And there are several ways to define and find these adaptive weights. And here in this work, we focus on random forest and nearest neighbors, who that has been shown to have quite good performance in several applications. So how does it work? I'm showing here an example in 2 dimensions. So we have our context being 2 features, x1 here, x2 here, and each square is a realization of our uncertain parameter. I'm showing with dark color, we can say maybe this is higher values. So here is where we have higher demand, and here is where we have lower demand. So how do we use these machine learning models to obtain adaptive weights? So now if we have in certain contexts, shown here with the red cross, using a k nearest neighbors and taking here k equal 4, we would look at what are the 4 nearest neighbors of X and assign them equal weights. And this regards all the other samples. And we say these are the most relevant samples now to take our decision, and we will find a decision that has the minimum average costs over these 4 points. With decision trees, we now partition the space into regions, into leaf nodes, and we check for a new context in what leaf node does it fall into, and assign equal weights to the samples in this leaf. Again, all the other samples are discarded. Now for random forest, we repeat this process over all the trees that we have in the forest. So this is a generalization of the decision tree algorithm in a sense. Now we say that what we want is to connect the decision to the context and to search over the different contexts. But as we can see here, the weights are piecewise constants. No matter where we are in this leaf, we will always assign the same weights, one third to these 3 observations. So searching over the feature space is actually a combinatorial problem when we work with forests or with nearest neighbors. So we are going to look for explanations using optimization models. Now we say that we are in a context x0, and we find our decision z0, and we have an alternative decision z alt that we want to explain. So the counterfactual explanation is in what alternative contexts that is closest to x0. This is why we minimize this distance between the explanation and our current context. In what other context is now z alt a good decision? And maybe there are a few ways that we can define what is an explanation here when we talk about decisions. Maybe we want Z-alt to have a lower expected cost than Z0. This is what we call relative explanations. Or maybe we want Z-alt to actually be optimal. So that means it's better than all the possible feasible solutions in this context. So directly we see that absolute explanations is a much stricter definition, and also leads to what looks like a complex bi-level optimization problem. So still, this approach is quite general, because here we don't really make assumption on the cost function C. In fact, it's not evaluated in the optimization problem here on the left. So we can apply it to both single and two-stage problems. And here I'm showing with expected cost, but we can also have similar definitions for CVAR objectives, for instance, to reflect the risk aversion. And using optimization for obtaining explanation is very flexible, because we can also have as many constraints as we want that define how the feature is allowed to change. Maybe we do not want to change all features, but only a subset of them. Or maybe we only want some of them increasing or decreasing, and so on. All right, so this is how to find explanations, the two types we define. But of course, here the difficulty is how do we track in an optimization models how these weights evolve as a function of x. And we propose to model this again as mixed-integer linear techniques. And we can do this for random forests and for nearest neighbors. So we can show, now define these weights as decision variables and track how they evolve with the context. So I'm not going to detail this formulation. In fact, I'm not showing the whole formulation for random forests, because we can adapt results that exist that have been actually proposed by Axel Parmentier and Thibaut Vidal in previous work, that in the predictive setting, so explanations in the not of decisions but of predictions. If you want more details, especially on this one, I encourage you to have a look at the paper, or maybe look online. Thibaut has some videos presenting it. And it's quite an interesting formulation. Every time you want to optimize over random forest or find explanations of random forest, it's quite a nice formulation. And for nearest neighbors, we didn't actually find a formulation to find explanations in the predictive setting, so we had to develop our own. And this is a relative explanation. So in the absolute case, now we have here a constraint that Z-alt is the argmin of the expected costs. So this is how do we obtain these explanations? Well, we just repeatedly find relative explanations, check whether they are absolute explanations or not, and if it's not the case, we restrict the acceptable space for our features and add the constraints, and then repeat this problem. Again, here I focus on expected costs. We also have formulations for CVAR. CVAR is a bit more difficult to actually formalize, because we need not only to track what is the CVAR, but also track what samples are selected. Because when we use CVAR, only a subset of all samples matter for the costs. Yeah, let's instead have a quick look at some results. So we have applied our methods to the shortest path example that is with real-world data, as we've shown earlier. And we also use it on 3, or rather 4, problems taken from the recent literature. So we have a multi-item use vendor problem, a two-stage problem where we first decide how much to produce and then decide how to ship to different locations. And we have a shortest path problem over square grids that we have for either expected costs or CVAR objectives. And what we will do is repeatedly sample contexts, train our machine learning algorithms, obtain a and then try to find the explanation. So we will repeatedly sample new contexts and try to obtain an explanation from this context by comparing to an alternative decision that is also randomly generated. So maybe the first question we can ask is, well, how much time does it take to actually obtain these explanations? And this can vary quite a bit. This is expected. It depends on what kind of problem you consider here. What is the size of the training sets? Are you using random forests or nearest neighbors? Do you want relative or absolute explanations? There are quite a few things that will impact the computational time. But maybe an interesting observation from this is that when you are using random forests to define your machine learning weights, adaptive weights, then the explanation problem scales actually very well with the size of the training sets and with the dimension of the contexts. So it is rather when we want to find relative explanation and actually absolute explanation as well. And this is mostly the size of the random forest. It will define whether it's hard or not to find the explanation. So another analysis we performed is to see, is it harder to explain hard problems and when? And here we consider the shortest path problem where we have square grids. So here we show the grid size. So this is a 3 by 3 grid. This is a 20 by 20 grid, and we want to find the shortest path between two corners. And we can see that for relative explanations, the complexity of the problem has actually almost no impact on the time it takes to explain it. However, for absolute explanation, we see this complexity increase, which is quite to be expected again, because we are solving a bi-level problem. So of course, the complexity of the lower level will impact how much time it takes to get the explanation in the end. So maybe there is a trade-off between relative and absolute explanations as we presented. And here is another perspective on this trade-off. In our experiments, we sample repeatedly contexts. So the first context where we start and get a decision, and a second context that we use to determine what is the optimal decision in this case. And then we try to explain this decision from the other contexts. And what we measure here is, are we actually recovering the direction that leads us to the alternative context that generates the alternative decision? And in our experiments, we see that when we obtain absolute explanations, we almost perfectly recover the direction that leads us to this alternative context. And with relative explanations, it's very often largely positively correlated, but not as much as 100% as in the absolute case. So maybe we have a trade-off between relative and absolute explanations, relative being much simpler to compute, and absolute maybe having a higher information power in terms of really guiding you towards where a decision is optimal. All right, so to conclude, I tried to give a quick overview on our work on how to explain decisions rather than predictions. So trying to look at the whole pipeline from context through machine learning and optimization and to decisions. How do we reverse the pipeline to link decisions back to the contexts? We presented the first approach that is actually applicable in very different contextual problems, maybe single stage, two stage, expected scores, and so on. And we have seen that for random forests that actually provide some of the best performance in many cases for the decisions, then it's also quite efficient to actually explain them. So they provide a very good model to use for data-driven predictions and decisions. And for future research, I think there are several, many directions we can take. The first one is maybe to try to speed up a bit the computations. So maybe using decomposition techniques if we want optimal explanations, or maybe we are happy with approximate explanations. And here we can reuse some of the rich literature in the machine learning community that have looked at how to provide approximate explanations. And of course, we can extend it to other types of machine learning or different types of pipelines for data-driven decisions. So I will stop here. Thank you very much for being here, for attending the talk. If you have further questions, feel free to contact me, or we have some time at the end. And we also have a preprint available online for this work. So thank you, and I will let the next speaker present.
Thank you so much, Alexandre. It was a really interesting talk. So now the next speaker is Tabea Röber from University of Amsterdam, and she's going to talk about empowering the user, finding regions of counterfactual explanations via robust optimization. The floor is yours, Tabea.
Thank you. Let me share my screen. Okay, can you see the slides?
Yeah, perfectly.
Okay, perfect. Yeah, thank you for the introduction. My name is Tabea. I'm a PhD student at the University of Amsterdam. I'm working in my PhD on the very broad topic of interpretable machine learning. And yeah, today I want to talk about our work on robust counterfactual explanations. And this is joint work with together with my colleagues Donato, Yannis, Rob, Ilka, and Dick. And yeah, explainable machine learning. So that's a very broad topic, and there's a big debate going on about what interpretability actually means. or explainability, if those two are the same, or if not, what's the difference. And many different approaches have been proposed recently on how we could explain machine learning models.
Tabea, the slides are
yeah.
not shared right now.
Oh, really? Oh.
Yeah, I just thought.
Now? Can you see them?
Now, yeah.
Okay. Yeah, so so there are many different approaches for explainability and interpretability, and we can roughly group them into basically glass box and black box models. So on the one side, we have the glass box models, which are models that are said to be inherently interpretable. So like linear logistic regression, rules, decision trees also, and maybe even k-nearest neighbor. And then on the other side, we have the black box models that we are trying to explain using post hoc explanations. And there we have model-based explanations, which are approaches where we are basically approximating a black box model with a more simple and more interpretable model. Then we have attribution-based explanations, which are feature importance methods and heat maps. And then we have example-based explanations, which could be prototypes, and counterfactual explanations also fall in this category. And in my PhD, I'm working on rules and on counterfactual explanations. And yeah, like I said, this talk is going to be about counterfactual explanations. And this is a relatively new method to explain black box models, or the outcome of black box models. And the first optimization-based approach to this was proposed in 2018, published in Harvard Journal of Law and Technology. And since then, many approaches have been proposed, and many more approaches have been proposed to generate counterfactual explanations. And there are also some review papers, and I actually believe that the one that I have the screenshot here of has recently been updated. And I would also like to point out the paper from Tim Miller from 2019 about the insights from the social sciences that we can use for explainable machine learning. And he is basically saying that counterfactual explanations is very similar to how we give explanations in real life or in everyday life. And therefore, it might also be a good option to explain machine learning models like that. So what is a counterfactual explanation? So let's say we have a training classifier and we have a factual instance or a factual point x hat that is predicted as -1, so the negative class. And then we are looking basically for the closest point that is, however, predicted to be in the positive class. So for example, here on the right-hand side, you could see the decision areas of a decision tree, and then we have the factual instance as the yellow square that's in the negative class, and then we're looking for the closest point to the factual instance that's in the positive class. And we can formulate that as an optimization problem. So we are minimizing some distance function between the factual instance and some point x, subject to the constraint that the outcome of the predictive model for x is greater or equal to some threshold. So this could be 0.5, for example, and then everything above 0.5 is classified as 1, and everything below that is classified as a negative class. So that's the basic idea of a counterfactual explanation. And a very prominent example is actually from credit risk scoring. So let's say we have this individual here with these characteristics. So age 27, salary 42,000 euros, and account balance 8,200. And this person, according to some predictive model, does not get granted a loan. So then a calculated counterfactual might be this one, age 27, salary 45,000 euros, and account balance 10,000 euros. And then the explanation could be formulated like this. If your salary would be 45,000 euros and your account balance 10,000 euros, then you would have been granted the loan. So that's a typical example that is often used. But now the question is, if we see this from the user point of view, it might be actually really difficult to reach this calculated counterfactual. So to really match this counterfactual exactly. So the question could be, what if the account balance, for example, would be a little less or a little more, like, for example, 9,985 or 10,009 euros. So these points are really close to the calculated counterfactual, but they don't match it exactly. So then we actually don't know if those are also counterfactual points or not. And that's especially in counterfactual explanations relevant, because by definition, we are minimizing the distance. So the counterfactual point that we get is always going to be at the decision boundary. So then a very small change might invalidate it again, basically. And so our idea was to kind of find counterfactual points that also remain valid counterfactuals after small changes. So the idea is basically to find a counterfactual point that lies in a set such that every point in that set is a possible counterfactual point. And here we can use some uncertainty set, like the L1, L2, or L infinity norm could be used for that. And this is how it would look like as an example. So again, these are some decision regions of a classifier, of a decision tree, and the gray areas, everything in the gray area is predicted to be in the negative class, and everything in the red area is in the positive class. So we have the factual instance again as the yellow square in the negative class, and we have defined the radius of the uncertainty set, and we're now looking for the closest box, basically, where all points of that box are in the red region. There are some other works in the literature that have the same idea of robust counterfactual explanations. And so the first paper here, they are modeling the noise around the counterfactual point with a normal distribution. And well, basically both of these papers, they cannot guarantee full robustness, and they are also not applicable to classification trees or tree ensembles. So for our work, the goal was to derive a method which guarantees robustness and is also applicable to decision trees and tree ensembles like random forest. And the optimization problem can be formulated like this. So we minimize some distance between the factual instance and some point x. And this could be L1 norm or L2 norm, for example. We are using the L2 norm. But yeah, and then it's subject to the constraint that the outcome of the predictive model for x plus any scenario in the uncertainty set is greater or equal to some threshold. And we faced some difficulties, which are that this formulation has infinitely many constraints. And what we could do is reformulate the constraint and then use duality. This is not really working for many non-linear classifiers. So we came up with another approach, an iterative approach, which is the adversarial approach. And I'm going to talk about that a little bit more. So in the adversarial approach, we have the master problem, which is a relaxation of the original problem with a finite number of scenarios. And naturally that provides a lower bound of for the optimal value of the original problem. And then we have the adversarial problem that finds us a new scenario in S, which violates the constraints for the current solution of the master problem. And we solve these two in an iterative manner. So the idea is we solve the master problem, and the optimal solution of the master problem X star might not be a feasible solution for the original problem. So there might be some scenarios that are in S but not in Z, for which the outcome of the predictive model might still be the negative class. So then we are solving the adversarial problem to find such scenario. and we add it to the set, and then we solve, then the current solution becomes infeasible, and then we solve the master problem again. And yeah, we do this a couple of times until the box, until we don't find any scenario anymore that violates the constraints. So basically, we have this box, and it, we're adding scenarios to it, and the box moves around until the complete box is in the feasible region. This is also what we display here on the right. So this is the same example from before, but now at every iteration we are visualizing the box, so you can kind of see how it moves towards the final solution. In our paper, we also talk about convergence, and we are showing that our algorithm converges if the evaluation function of the machine learning model is Lipschitz continuous. This is the case for logistic regression and for neural networks with a ReLU activation function. This is, of course, not the case for decision trees, which are not even continuous. So what we are proposing is to define an alternative classifier that is Lipschitz continuous and has the same decision regions as the decision tree. And then another thing that we propose in our paper is to use a heuristic variant for trees, which is to restrict the solution to be in one leaf. So the idea is that the adversarial approach can be quite computationally demanding. So it might take a long time to find the optimal solution. And so what we could do is we could say that we accept a solution that's only in one leaf. And then the idea is that we can solve the master problem for each leaf separately and then choose the solution with the best optimal value. And the drawback of that approach might be that the solution we find, or the box that we find, that it might be further away from the factual instance. So that's also what we visualize here. So on the left, you see the solution with the heuristic. So the box is in only one leaf, so it's in the bottom right corner. And then on the right-hand side, you see the solution with the adversarial approach. So here you see the boxes overlapping several leaves. And with that, the box can be much closer to the factual instance, which again, from a user point of view, might be more handy practice. Yeah, then we tested our algorithm on 3 different data sets with different numbers of features. So we have 4 features, 8 features, and 34 features in these data sets. And we've trained a couple of different models with different complexity. And basically what we did is we used 20 factual instances. And for each, we calculated the counterfactual using the L infinity norm as uncertainty set. And here are the results with the radius of the uncertainty set to 0.01. What we report for every data set and for every model is the average computation time and the number of iterations, the average number of iterations, and the number of early stops. So for example, if it says here 2 early stops, that means in 2 out of the 20 cases we had to stop early because we hit the time limit, which we set to 1000 seconds. So that's about 15 minutes. And then in the parentheses, we report the average radius for the early stops. So even if we don't terminate, if the algorithm doesn't terminate in the time limit, we can still find a solution. The radius is gonna be smaller than what we had previously set, which was 0.01. But yeah, even if we have to stop early, we can still provide the user with some set of counterfactual explanations. And generally what we see in these results is that as expected with increasing model complexity, increases also the computation time and the number of iterations. However, the number of features actually does not make a big difference. And then we also did that for radius of 0.05. Yeah. We also did that for radius of 0.05. The results are similar. Of course, computation time goes up, number of iterations as well. And with that also the number of early stops, especially for the more complex models. Yeah. To conclude, we showed how we can derive robust counterfactuals by using a robust adversarial approach. To guarantee convergence, the evaluation function of the machine learning model has to be Lipschitz continuous. And we show how we deal with this in the case of decision trees. And we test our algorithm on several data sets with several machine learning models. And actually with the L infinity norm as uncertainty set and the L2 norm. And then for future work, we are thinking, or we're looking into speeding up the calculations of the master problem, and to also look into categorical features, because as of now, the data sets that we've been using only have numerical features. And yeah, please get in touch if you have any questions or remarks or comments. And other than that, thanks for your attention. And yeah, I'm happy to answer questions to the best of my knowledge at the end of the session.
Thank you so much, Tabea. That was really interesting, really nice. So we will go on with our final speaker, and he's Defeng from Polytechnique Montreal, and he's going to talk about revisiting local branching with a machine learning lens. All yours. Defeng, I think you're you're muted because we can't hear you.
Can you hear me now?
Yeah, now yes.
Oh, great. So can you see my screen?
Yes.
Perfect. So yeah, hi everyone. I hope at this time you guys, so everybody is not getting so tired. So as the third part of this seminar, I'm going to present one of my PhD work, which the title is Revisiting Local Branching with a Machine Learning Lens. And by the way, my name is Defeng, and I did my PhD at Polytechnique Montreal with Professor Andrew Lodi, and this is our one of our joint work. And in this, so we are Canada Excellence Research Chair in data science for real-time decision making. So in our research group, what we do is we aim at developing new tools and methodologies that will allow enormous volume data from multiple sources to be processed and analyzed in real time, and in order to obtain usable knowledge to automate decision making. And we solve many different kind of operation research problems, and many sectors that could benefit include transportation, management, energy, healthcare, and manufacturing, as well as supply chain management and logistics. And in this project, we are talking about combinatorial optimization. So a large range number of real-world decision problems are combinatorial optimization problems. The examples include the problems from supply chain, packing, scheduling, and logistics, and etc. And usually we apply mixed integer programming techniques to solve these problems. So here is a general formula for a mixed integer program. So we have an objective function with a set of constraints and a set of variables. So since many of combinatorial optimization problems are NP-complete hard, so it's very difficult to solve. So in practical, we develop different methods for solving MIPS. For example, branch and bound are the backbone of modern MIP solvers. So where we split the solution space into subspaces by branching, and we generate a branch and bound tree with with different nodes until we find the optimal solution. We also have cutting plane techniques to increase the lower bound of a MIP problem, where we solve a relaxation of a MIP problem by removing the integrality of the variables, and we solve the relaxed LP problem, and then we apply cutting plane techniques to optimize the relaxed problem. And we also have heuristics, and in this work, we focus on the primal heuristics for solving MIPs. And so primal heuristics play a critical role in exact MIP solvers. The idea is that in MIP, indeed, we are dealing with solving problems to optimality, but at the same time, building a MIP formulation for a problem and the resolution of such a model by MIP solvers like Simplex, Groovy, or open source Skip is definitely built around multiple things. And one of them is to compute and update feasible solutions as soon as possible for two reasons. First of all, you can use primal solutions to prune nodes in the branch-bound tree, which is the basis for modern MIP solvers. And pruning nodes with early primal solutions can help reduce the size of the branch-bound tree. And besides, while MIP solvers are guaranteed to find the optimal solution given sufficient computing time, however, real-world applications typically require finding good solutions in the MIPS in the solution search to enable faster decision making. So in 2003, my PhD supervisor, Andrew Lodi, and Matteo Fischetti, they proposed a very well-known local branching heuristic method, which is local branching. And the idea is actually to firstly define a series of solution neighborhoods and then explore them by recursive calls to a MIP solver. And today, what we are going to do is we are going to revisit it here through a machine learning lens, in the sense that we will run over this method and use it as an example to demonstrate how MIP algorithms can be improved by exploiting machine learning techniques. So first of all, let me first remind you what local branching is about. Given a MIP model with a form of minimizing an objective function over a set of constraints, and we assume there exists a group of important decision variables which are binary variables. And in the local branching heuristic framework, what they do is they start from a feasible solution, X bar, and they define a local branching constraint on the bottom of this slide, saying that so the number of assignments of binary variables in the current solution can change up to k, which means that they are defining a solution neighborhood composed by solutions where the Harman distance at most k from the current solution. We call the solution neighborhood defined by these constraints as the local branching neighborhood. And by adding this constraint to the original model, we will have a sub-MIP problem and a sub-solution space of this sub-problem. In local branching heuristic, a generic MIP solver is used as a black box tool to explore a series of such kind of local branching neighborhoods, and it looks for improving solutions from that. So at the end of this slide, you see what we call the basic version of the local branching constraint, which means that we are computing the number of changes in the current solution X bar with the binary support defined by X bar, capital S bar. We count both the transitions from 0 to 1, so the first part of this local branching constraint, and also the transitions from 1 to 0 of the variables, which is the second part of this constraint. So the strength of this heuristic framework is that there is a clear integration of the local search meta heuristic within mixed integer programming solvers. And we are defining these solution neighborhoods and exploring them internally as a new core in the MIP solver. The scheme is exact in nature, so which means you can do local branching, you can do left branching with the local branching neighborhoods, and you can also do right branching to solve the resting part of the solution space. So, however, there are still some limitations. First of all, in the local branching scheme, the default value of the size of the neighborhood, where we call it k, is fixed by a constant value. A typical setting is 20. This is chosen by some human tuning. So the authors of the original local branching paper did some preliminary experiments, and they found out that so 20 is a good value for most instances. So they fixed it once for all. However, our new observation shows that the potential best value of the size of the neighborhoods is really dependent on your instance at hand, and we believe there is a strong correlation between the distributions over instances, the resolution states, and the best value of k. So this is not fully explored by the original local branching paper. And so we analyzed the relation between the size of the neighborhoods and actual performance of local branching heuristic. So in this example plot, the x-axis is normalized neighborhood size. So from 0.0 to 1.0. And for the y-axis, the first subplot on the upper side reports the objective, and the second subplot on the bottom gives solution solving time. And as we can see in this example instance, the size of the first local branching iteration is critical to the performance of the left branch. So which means when the neighborhood size is small, let's say smaller than 0.2 or 0.1, the computing time spent for solving the local branching subproblem is very, very small, as you see in the second subplot on the left hand. And at the same time, the improvement you can obtain, so the quality of the solution would not be particularly good, as you can see in the first subplot. So by the way, we suppose we are solving a minimization problem. So as long as you are finding an improving solution, your objective function, so the objective value of your objective function should be getting smaller and smaller. So on the other hand, if you increase the neighborhood size, so the solving time, so the solving of the local branching subproblem can be very expensive. However, there is a sweet spot where the local branching subproblem can be solved very fast, and the solution improvement is still very high. So in this project, our target is to identify a good neighborhood size of this sweet spot for each given instance. And so we want to optimize over the neighborhood size k. That is to say, given an instance, we would like to optimize the value of k to maximize the performance of your local branching heuristic. And optimization over k can be formulated into an optimization problem, and where we have a cost function defined to evaluate the cost of your local branching algorithm. And this cost function takes a MIP instance and a set of k as input and computes the cost of your local branching algorithm. And as a matter of fact, this problem is analytically solvable since the cost function is never known and defined. And in practice, what we can do is you can use black box optimization techniques to search for a good k. For example, there are like model-free methods such as grid search. There are also Bayesian optimization techniques. However, the limitation is that the function evaluations for each instance are too expensive for practical uses if you apply the above black box optim methods. So in this project, we are trying to apply data-driven methods to tailor the size of the local branch neighborhood. So our first idea is that with the assumption that the best K is dependent on the distribution of the instances and the resolution states. So if I can ever have a machine learning model, so leveraging the data over the distribution of the instances, a model can be trained to predict the value of K that induces a good performance of your local branching heuristic. And today we are going to briefly introduce two ideas. The first one is to learn to predict the first key value, so the first local branching neighborhood of the first local branching, the first iteration of your local branching algorithm by a regression task. And in the second part, we are going to employ reinforcement learning for adapting the neighborhood size in the subsequent local branching iterations. So our framework consists of this two-phase strategy. In the first phase, we define a regression task to learn the neighborhood size for the first local branching iteration. And within our methods, the size is predicted by a pre-trained regression model. For the second phase, for the subsequent local branching iterations, we leverage reinforcement learning and train a policy to dynamically adapt the neighborhood size. And the exploration of each local branching neighborhood is the same as your original local branching framework. And a general MIP solver will be applied to update the incumbent, the primal solution. And so the overall scheme is also exact in nature as the original local branching framework. So although tuning it into a specialized heuristic is also trivial. So for the first part, our proposal is to learn to predict K0 by a regression task. The idea is that we train a regression model that maps the feature of a MIP instance into a K0 star, which is the label of the best K0. And the whole process can be divided into 3 steps. So data generation.
You have like 2 minutes left.
Okay, sure. Let me quickly go over this this framework. So we have 3 steps: data generation for computing the label, where we apply black box optimization to estimate this K0 star, and then we train the model, and finally we apply the trained regression model to predict the K0 for any new instances. And so here are some experimental results. So we evaluate our model with like multiple data sets. So some of them are, let's say, specialized MIP problems. And we also apply this framework to some MIP-lib instances for general MIP setting. And our results are showing that the generalization performance is remarkably good. So we are comparing our algorithm with the local branching baseline, so which are the local branching base. So our local branching framework is LBSRM as the third column. So our performance, which are, for example, here are we report the primal integral and the primal gap. So our primal integral and primal gap are both better than the local branching baseline. For if you're interested in these results, you can check our paper online. So for the second idea, we are using reinforcement learning for adapting the K for the subsequent local branching iterations. So here we don't have time to present the technical details, but the idea is, so the reinforcement learning agents can dynamically change the value of K based on the feedback of your local branching resolution results from the last iteration. So the result is also showing that our performance with RL can also achieve even a better performance than the local branching baseline. So our conclusion is that the amount of opportunities for using local machine learning in combinatorial optimization or mixed integer programming is very high. The key message here is MIP solvers are a collection of algorithmic ideas, some of which are inherently heuristic, thus can clearly benefit from data and learning. So we are only at the beginning of the road, and the challenges are many, but it looks very promising. So thank you for your attention.
Thank you very much for the great presentation. We are running a bit late, but we have time for one or two quick questions. So if you have a question, please write in the chat or raise your hand and we'll give you permission to use the camera and microphone. Okay, it seems like there are no questions. Thank you to all of our three speakers. And we are back next week with the regular seminar on
One
Monday.
moment, I don't know.
Is there a question?
No, it seems, but yeah.
Hi, can you hear me?
Yes.
Ah, perfect. I would have a question for Alexandre Forel. The very interesting topic, actually. So I was wondering, it was very quick. So you said for your absolute explanations, you need this. So you model it as your alternative solution is an optimal solution. So how do you handle that? I guess you cannot use KKT conditions because you don't have an continuous, so you have integer problems. So how do you handle this that the alternative solution is optimal?
Yeah, thank you very much for the question. So you are right. We are trying to work in general situations where we don't assume a specific structure of the decision problem. So not necessarily linear. So we cannot use some of the common tricks there. Well, we do study when we can use them, but we also study when we cannot. And so what we do is we are repeatedly solving the relative explanation problem. The relative means that you find the context such that your alternative decision is better than your current decision. And for an absolute, it should be better than all the others. So you know that if you have an absolute explanation, it's also relative. So we are repeatedly finding relative explanations, checking if it's also an absolute explanation. If it's not, then we remove this region from the acceptable space and solve it again, and we find another relative, and so on and so forth. And we know that if we find the closest relative explanation, we check it's also an absolute explanation. We know it's the closest one.
Ah, yeah,
I don't know
interesting.
if that makes sense.
Yeah, it makes sense. And is it also possible if you so somehow your alternative solution is a full solution, but you could have maybe the case that you want to know, is this edge used in an optimal solution? So what would be the counterfactual such that this edge is used? So your alternative solution is not complete. So some of the variables are still variable. Would that be possible, or is it? Do you get nasty products of variables in your model then?
Okay, yeah, that's an interesting point of view. So when we work with explanations, we can in an optimization model, we can very easily add structure to the context. So we can say what features are fixed, what features can only increase and so on. But in the version we have now, we cannot really enforce structure on the decision, and that could be an interesting point. Yeah, but usually what we start with is a solution, so it's given.
Yes.
Right?
Yes.
So,
Okay. Thank you.
so I don't know how it would look like, but thank you. That's interesting suggestion.
Yes, I think we have one more question. Martin, you should be able to speak.
Hi, can you hear me now?
Yes, hello,
Yes.
Martin.
Hi, Alexandre. So it's maybe a connected question to the previous question. So, you know, when you're using this, you then need to actually come up with this alternative solution, right, that you have discussed. And maybe that's actually difficult for a user, right? So would it be possible that to only specify maybe parts of the solution and then say, okay, you gave that routing example, right? So maybe not the full path, but maybe I just say I would have gone through this point or something like this, and then use that part of information. Maybe that's a bit related to the previous question. And my other question is more like a general question. Of course, the question is always what's a good distance measure here, right? Obviously, I think also in Tabea's presentation, she gave this example of the age being a feature, right? And there's nothing you can do to change the age, right? So what is a good way of defining these distances, right?
Yeah, thank you for the question. So I think the first one is yes, really related to what Yanis asked. So for us, the alternative decision is really a starting point. So it's given. We are not really optimizing over it. I would really need to think about how do we only partially specify it. I think it's an interesting point. However, when we, for instance, we already have this a bit because when we explain, for instance, two-stage problems, we only need to specify the first stage alternative decisions and not the scenario decisions. So that's what maybe a partial answer. But in the more general case of having only a partially given alternative decision, I'm not too sure. Now, in terms of distance measure, yeah, I think this is always it's always going to be very application specific. I don't think there is a general way of doing it. How do you compare changing your age versus changing your income in terms of distance? Yeah, that's very hard. Yeah, I think maybe the best is to try out some distance measures and see what kind of results you obtain. Thank you.
Okay, thanks.
Thank you very much for the questions. I think.
Or maybe Tabea has another point of view on distance measures.
Yeah, no, I agree. I think it's a really difficult thing to determine at this moment, and also it's really yeah, context dependent, I think. Yeah.
So thank you very much for the questions, and thank you to the speakers. And
We'll see
we'll
you
be
next
back
week.
on Monday.
Thank you. Goodbye.